Okay, so good morning, everybody. We are going now to see the third lecture by Percival. So I guess without further ado, just take it away.
Thank you. If anybody is in here for the chem exam, that is not in here now. You need to go upstairs. Just checking to see if anybody gets up. No, we're all good. Okay. All right, so this is me going off on a complete tangent because I asked, but when I was writing the lectures, I thought, what if I was sending my graduate students here? I'm not, because I'm lecturing. I can do this. I can teach them all this later on. But what would I actually want them to come back with? And at the moment, with the state that cosmology is in, and the focus on testing models, comparing models, and a lot of the focus is on priors, statistics, I thought I would want them to come back with a really good understanding of the overview of what people are using now as statistics in cosmology. So this is that lecture. I wrote it all new, which means it's almost certainly more likely than anything else I say to contain errors and bugs. So let me know if you spot anything. So a lot of data analysis can actually be described as data compression. And why do we want data compression? Well, because having a small amount of data to deal with really speeds up the analysis, and it reduces any numerical contributions to errors, and it really helps us diagnose problems. So by data compression, that could just be the calculation of a binned power spectrum. And it could help us diagnose problems is because we have some idea of what the power spectrum should look like from previous surveys. And we can see if there's been a major catastrophic problem with our data analysis, because the power spectrum we calculate looks very different, for example. The compression can be through fundamental assumptions, like the homogeneity and isotropy of the universe, and it could be more nuanced. If you know your model has a particular form, then that's the model you want to test, then you only need to use the data in a way that's going to be able to test that model. So if your model only, for example, depends on one particular moment of the distribution, you might want to compress your data into only that moment, so you have a reduced set of data to compare to the model. Okay. The compression might not be through something you know. You might just want to use one of the basic techniques of data compression, one of the basic numerical techniques. For example, the Kuhn and Louvre transformation, principal components analysis, singular value decomposition. The idea behind all of these is if you have a large amount of data, and you can imagine the covariance matrix, the relative errors of all of that data, and you want to compress that data by looking at some reduced vector space of that large data space, then each of these methods is a different way of finding an orthonormal basis, an orthogonal basis that will span that space, and that you can reduce the number of vectors of data that you're looking at within that space. One of the problems with applying these numerical analyses tools is that they almost all need an estimate of the covariance matrix to start from. So if you have 10,000 data points, you would start with a 10,000 by 10,000 covariance matrix, and you would compress that down into, let's say, 100 by 100 covariance matrix of, if you were doing principal components analysis, the top eigenvectors or the top eigenvalues, the eigenvectors of those eigenvalues. So in many cases, a pure numerical data compression is very difficult to do. Optimization, weighting, is really just part of data compression. You want to do that compression optimally, but sometimes you split out the optimization part from the compression part. And for example, if you just took your galaxy survey and you put it on a grid and you calculated a Fourier transform of it using a fast Fourier transform algorithm, and you converted it into a power spectrum, that would be treating each grid point in that analysis as being of equal value in the calculation of the power spectrum. But our expected density of galaxies varies from place to place. And so it's not optimal to treat every patch of your observed universe as being equal contribution to the power spectrum. So there's something called the FKP weight, after the first derivation, Feldman-Kaiser-Peacock, that weights different patches of the universe differently depending on the expected density of galaxies within them. And in particular, if you had a patch of the universe where you expected only a small number of galaxies, you would weight those galaxies equally, because that patch would be what we call shot noise limited. Whereas if you had a patch where you expected there to be a higher galaxy density, say it was at lower redshift and they were easier to observe, then you might weight by 1 over n bar 1 over the expected density, in order to basically reduce down the relative weight of this, because this is what we call sample variance limited. This relatively balancing of different patches would be included in a numerical optimization if the numerical optimization was set up to include this information. So if you were doing a full numerical optimization of the densities in real space to calculate your power spectrum, then you would automatically get the FKP weighting. But that's very difficult to do, and therefore there is a case for putting in these kind of optimizations separately. So if you download the DESI catalog and you want to calculate a power spectrum from it, you will find a column in that file that contains the FKP weight, which will be doing this for you. Okay. So we've compressed our data, we've optimized the compression, we're happy that we haven't thrown out too much information, and we've kept pretty much everything we want to do. Now we want to start making inferences about a set of models. We want to compare the compressed data to the models. This is done through the likelihood, which is the probability of the data given the model. This is the easy one to calculate, because that given the model is a very powerful statement in this conditional probability. It is common to assume a Gaussian distribution for the likelihood, assuming your data is distributed Gaussian in a Gaussian way from the model. And the power of this given the model is that all of the terms in the likelihood are dependent on the model, including the covariance matrix. So formally, for this likelihood, the covariance matrix should change with every model being tested, because every part of this likelihood depends on that model. Now, this is a very nuanced statement, so if we go back to our example that I was saying before of measuring the power spectrum, the way that that power spectrum is measured often makes assumptions that cancel this change in the covariance matrix. So let me just leave that there, because we've got a lot of material. Ask me about that later if you want. Okay. Given this likelihood, we now want to make inferences about the universe. And this is where things start to get complicated and a lot of people come unstuck. There are two different ways to do this. There is the frequentist way, which is to view probabilities as a measure of the distribution of results from a long run of experiments. So I've spoken to a number of statisticians, and they got pretty excited about the cosmology way of doing frequentist analyses, because we can actually consider there being different universes right from the start. And if you're doing frequentist statistics for a biostats type application, and you want to replicate your clinical trial, it's actually quite difficult to define how you would replicate that trial. Would you have different people from different bands, and so on? Whereas we have a pretty straightforward way of thinking about having different universes. The Bayesian approach is to view the inference as wanting to give you a subjective degree of belief about your hypothesis, given the data you've got and any prior knowledge you have about the models, the universe as a whole. And this is actually a very different problem that you're trying to solve. To see this another way, consider that Bayesian analyses lead to credible intervals defined as a range in a parameter that you're interested in, such that there's a probability gamma that the parameter falls within it. Gamma is what we call the coverage probability. So this is your post-experiment, post-prior degree of belief in that parameter, and your degree of belief, if it's a 67% credible interval, is that the truth lies within that interval. Frequentist analysis instead lead to a confidence interval. This is the statistical definition of credible and confidence intervals. If you go in the cosmology literature, you'll find these terms being misused very regularly. But frequentist analyses lead to a confidence interval, and that's defined for a repeat. It's just a procedure for finding this interval. But the idea behind this is that if you repeated the experiment, say 100 times, and you did this procedure for every experiment, then if it was a 67% coverage probability, 67% of those repeated experiments would have the truth within the interval you have determined. This is conceptually a lot more difficult to understand than the degree of belief, and we're going to see an example in a few minutes, which shows how complicated this can get. But the interpretation in the literature is mixed and poorly mixed and incorrectly mixed. So you will see tests of Bayesian credible intervals where the test is whether or not in repeated experiments, often described by doing the analysis using mock catalogs, whether or not the true value of those mocks is within the credible interval. And that's treating a credible interval like a confidence interval. You're doing a wrong test on it. In a Bayesian sense, the credible interval should not have to contain the truth in repeated experiments, as described by basically doing a whole series of mocks. You will also see confidence intervals being interpreted as degrees of belief, not actually as they are an interval defined for a series of different experiments. And to add to the confusion, if you're careful, you can define intervals which work as both credible intervals and confidence intervals with the same limits and the same coverage probability. Okay. Any questions? We good? All right. So, Bayesian analysis all comes down to Bayes' theorem. I'm not the first lecturer, even in this summer school, to show this equation. It is so ubiquitous and common in data analysis. You take your likelihood, you multiply it by your prior, and that gives you your posterior. The posterior is the probability of the model given the data. That's what you want to be able to make basically statements about your degree of belief from. You have the data, that's your given. It's the model you want to understand, and that's what the posterior gives you. If you want to understand the posterior in basically an interesting parameter, say phi, and you've got psi as being a series of parameters that you consider not to be interesting, then we do what's called marginalizing over them. We basically take the posterior and we integrate out the uninteresting parameters. The prior is the Achilles heel. It's the weak point of a Bayesian analysis. You cannot do a Bayesian analysis without a prior. And it's supposed to indicate previous knowledge constraining the model. Sometimes this is possible. Many times it is not. And if the likelihood dominates the posterior, it does not matter. If your constraints are so good that the likelihood is so tightly constraining compared to what you want, then everything is good. But in many cases in cosmology, we're not there because we are pushing the bounds with an experiment of what we want to know. Our experiments rarely give us a really tight, many sigma result that tells us this is what we want, and it doesn't matter what the prior is. You'll get that interpretation out anyway. Typical distributions adopted for, so the prior ideally would be what your previous experiments tell you about these parameters. But in practice, the prior tends to be, here's a set of parameters. What distribution am I going to assume for those parameters as I basically deform the posterior? Typical distributions include uniform. I'm going to basically calculate my Bayesian interpretation having omega m between 0.1 and 0.4. And I'm going to consider that to be the prior. It can be Gaussian. Here's a parameter. It's a bias parameter. I think it's around 2, but plus or minus 2. I'll put that in as a Gaussian prior. The Jeffreys prior is very interesting. Each of the uniform and Gaussian priors, you would actually change the prior if you change the parameter. If instead of omega m, I used omega m h squared. If instead of omega m, I used omega m cubed, and I had a uniform prior on it between certain intervals, the actual effect of it on the posterior would change. The Jeffreys prior is the prior for which this isn't the case. It's defined using the Jacobian of transformations, and it's defined in such a way as it actually gives you the same prior no matter which parameter you're choosing. And that's the beauty of it, and that's why for many statisticians it's the go-to prior of choice because it has this property. And as I said, you can also choose a prior which allows you to define basically a frequentist matching. You can define an interval in the parameter that works as both a credible and a confidence interval at the same coverage probability. So we have found in cosmology recently a number of occasions where the prior matters for the analysis we do. And we in cosmology have started to use two different ways of splitting this dominance of the prior, this importance of the prior. We've defined prior weight effects, and these are standard way that you might think a prior would change a posterior. It basically changes, it moves the maximum a posteriori parameters, i.e. the peak of the posterior, away from the peak of the likelihood. So your prior is basically having a significant effect on your inference that you're making. The prior volume effects, they are defined such that the choice of prior moves the marginalized parameters away from the maximum in the posterior. So now we've got the idea that if we have sort of a long tail in the posterior and we average to give us the average value of the parameter in the posterior, it is different from the maximum in the posterior. These are all really just prior effects. They just mean that the prior is starting to dominate your posterior, and none of them are particularly good in the case. And in this case, what you're really saying is that my data are not good enough to constrain my model. But cosmologists don't let them stop them making inferences. So this is an example. I'll actually show this in context in the next lecture, but it is basically the DESI collaboration full fits to the power spectrum. We're trying in this slide, in this plot here, trying to measure the matter density. This data point and the error bars show you the averaged value of omega m from the posterior, whereas this shows you the maximum posterior point. So in this case, we've got these prior volume effects coming in where the marginalization is leading to a difference in the inference we would make compared to the posterior maximum. Okay. So another example to show you where this all gets really complicated is if you consider that your covariance matrix is now also an estimate. It is rare in cosmology, as in any experimental physics, that you're in a situation where you know the errors on your data perfectly. you will almost always have an estimated covariance matrix, and that estimated covariance matrix should in many cases be considered as a draw from a random variable itself, so it should be considered part of the data. If, for example, you've used a jackknife method to get your covariance matrix, or it's constructed from simulations using the standard formula that looks at the variance between different simulations, then you will find your covariance matrix is drawn from what we call a Wishart distribution. This is just another statistical distribution from which you can draw like a Gaussian distribution, but this time for matrices, you can draw matrices and have a matrix as a random variable. In this case, the standard statistical way to proceed is to consider that the data vector includes the estimate of the covariance matrix, and the model that you want to fit includes both the model itself and the true covariance matrix that you want to understand from the data. Actually having both the data and its error as unknowns is a classical problem in statistics wrestled with by some of the greats of statistics, Fisher and so on, back in the 1960s when they were setting up all of the Bayesian formalism. Okay, so some of you might have heard of something called the Hartleb factor. This comes from this picture where we have both the data and the covariance matrix having an error on them. And for a covariance matrix drawn from a Wishart distribution, if you invert it, you get a biased result. So in exactly the same way that if you have a set of data and you look at the expected mean of that data, expected value of x, then that basically does not commute in a way that if you took 1 over the data and looked at the expected value of 1 over the data, that is not 1 over the expected value of the data. So if I took a string of random variables and I wanted to know what the expected value of 1 over x is, I would basically take 1 over each of those variables and take the expected value. I would not do 1 over the average value in that set. And that's because 1 over the expected value is a biased estimator for 1 over x. In the same way, once we have a covariance matrix drawn from a Wishart distribution, then the inverse of that covariance matrix is a biased estimator of the inverse. And this can be corrected by something called the Hartleb factor. It depends on the size of the data points and the error in the covariance matrix defined by the number of simulations or jackknife realizations you use to calculate the matrix, and the size of the matrix, which is the number of data points, ND. If you basically multiply your covariance matrix by this, then the inverse stops being biased. So this is commonly applied when you have a matrix drawn in this way, but just applying this factor is not actually consistent within a full statistical framework. And to understand how to do things properly, we have to go back to the start and say, okay, well, we're doing a Bayesian analysis. Our data and now our covariance matrix have to have a prior on them. And there are a number of different choices now for that prior because it's now a prior in a Bayesian analysis. There is the Jeffreys prior, which is this one with a property that your parameterization doesn't matter. There's a slight change in it called the independence Jeffreys prior. This was actually the one used by Celentine and Heavens in a great paper in 2016 looking at this problem. Other choices are available and had been advocated in the statistics literature going, as I say, way back to the people in the 1960s that were doing Bayesian analysis for the first time. If you take the independence Jeffreys prior, as Celentine and Heavens did, you calculate the posterior, you integrate to marginalize out the covariance matrix once you've got the full matrix. Then you end up with a posterior which doesn't now have a Gaussian form, even if you assumed it was Gaussian to start with. It is a multivariate t-distribution with a dependence on the size of the matrix and the number of simulations you use for the covariance and so on. If you work through and calculate the covariance of this distribution, you find that basically this Hartleb factor comes back in. So doing the full process with the independence-Jeffreys prior works very well. But if you wanted to approximate it with a Gaussian posterior, you could just apply the Hartleb factor, and that would work well. But this is not the only situation thing you can do, because Bayes' theorem tells us we need a prior for the covariance matrix. So if instead we took a prior which was the determinant of the matrix to some random or any integer m, any real number m, and worked through the same Salentin and Heavens procedure, then you would find that you ended up with a covariance for your data in the end that depended on exactly what the prior was you adopted for your covariance matrix. This is really the curse of Bayes' theorem, that in many of these situations, you're not quite sure what prior to take. And actually, that prior is very important for the inferences you then make. So in this situation, you can take a prior on the covariance matrix, and exactly which prior you take will lead you to a covariance, basically a width of your credible intervals, which really depend on that prior that you had to start with. So one alternative to taking the independence-Jeffreys prior, which we explored in this paper, was actually defining M to be a matching prior. So this is a way of putting a prior on the covariance matrix, which allows your credible interval to also work as a confidence interval, at least to first order. In that situation, the interpretation of the error bar can work both ways from a frequentist or a Bayesian standpoint. And we did this, we defined this matching prior, and we found basically you have, again, a standard t-distribution solution, but now with a different width. And the interesting thing about doing this is that when your credible interval now equals your confidence interval, all those incorrect inferences that people like to make, like repeating the Bayesian analysis on a whole series of mocks and seeing if the truth of those mocks lies within the intervals, actually works and is an okay thing to do. Because now the interval that you're quoting is both a credible and a confidence interval. It tells you not just your belief, given the experiment, on what the truth should be. It also tells you that if you repeat the experiment many times, this works as a frequentist confidence interval as well. So we think this was quite a neat thing to do. Okay. All right, moving on. Okay, so this is hopefully more familiar with you. Basically, the idea for the next bit is how do we estimate the posterior? You all know we do Markov chain Monte Carlo analyses, hopefully. Just to recap quickly, we want to explore the posterior surface. You've chosen your prior, you've got your data, you've calculated your likelihood, or you have a routine that will calculate your likelihood for a whole series of models that you want to test. You have decided you want to fit only flat models, which is basically a prior on the total energy density, that it is basically at the critical value. There's a set of parameters you've chosen. You've decided the dark energy equation of state will be parameterized by 2 parameters, or 1 parameter, or no parameters, it's lambda. You've made these prior assumptions about the set of models. You've made the prior assumptions about the set of parameters you want to vary, and you've made a set of assumptions about how you're allowing them to vary. You're having a uniform prior in the matter density and this range of values, for example. So now you want to explore that space of parameters that you've got left in your set of models using the data that's available to you. And so you want to sample that space. And we do this with something called the Markov chain Monte Carlo method. Basically, back in the day when I started in cosmology a long time ago, people were still using grids to explore these kind of multidimensional surfaces. But when you have 10 parameters, and even if your grid is quite coarse, so you only want to look at 10 values of those parameters, suddenly you have 10 to the 10 times you have to calculate your likelihood. And all of a sudden it becomes prohibitively expensive. So Markov chain Monte Carlo methods are a way to explore this kind of surface by building up a random chain of points that samples the important part of this multidimensional surface. And the traditional way of doing this is something called the metropolis algorithm. Basically, you build up a chain by starting at one point. You have some basic trial distribution, some way of going from one point in your model space to another point in your model space. You accept that next point if it is basically has a higher posterior value. You reject it on a probabilistic basis if the posterior is lower. And if you reject it, you basically stay at the point you are at. So in an example chain, you would start here, you would look at this point, it is basically a higher in the posterior, you would move there. You might then try this point, it's a higher posterior. You draw a random variable based on the ratio of the posteriors. If that was like lower, you wouldn't go there, you would stay at this point and then you try another jump and that might be more accepted. And so your chain in this case would be x1, x2, x2, x4, so on. Now there is a theory that says that basically for any symmetric proposal distribution after an infinite number of steps, this chain will be representative. The density of samples in the chain will be proportional to the posterior that you are basically looking for. So this is now the workhorse routine that we all use to explore posterior surfaces. The trick is basically to determine the jump size, basically the way that you move from one point to the next, such that it's not too broad, where the chain would lack mobility, and it's not too narrow, in which case you're not exploring the surface efficiently. And roughly, as an order of magnitude, you want about one jump in 4 to be accepted to get the right balance between these points. But this is all done automatically for you in a large number of different packages out there. So really, you just need to know the understanding of what the package is doing rather than the details of the package. There is a problem of burn-in where you might think the result is dependent on where you started the chain. That, again, is removed in most packages. If you know the gradient of the posterior, you can speed up the exploration of the surface, which is why a lot of the new developments are in code that does auto-differentiation, where suddenly now you can calculate the derivatives of your posterior and you can do more efficient samplings then of the surface using things like NUTS, the no U-turn sampler, microcanonical samplers, different ways of basically exploring the surface and making these chains be calculated more efficiently. And you're going to hear this in the lectures after the break, but languages like Julia or JAX that allow this order differentiation are really changing this field quite significantly at the moment. Okay. Also, to speed up the posterior calculations, it's common to do analytic marginalization. I'm not going to go into the details, which is why I don't mind if you can't read all of the equations. But basically, if there's a parameter and you think the posterior has a Gaussian dependence on that parameter, then you don't need to numerically explore that additional parameter. You can just analytically marginalize it out every step of the case. And this, again, speeds things up. Okay. I'm going to speed up a little bit. Bayesian model selection is kind of interesting. A lot of what we want to answer in cosmology are questions like, is the universe flat? Is it lambda? These are model selection questions. I want to compare lambda CDM against a different set of models. And in the Bayesian sense, it's kind of natural to include the model itself as a parameter. Let me have a parameter 0 if it's lambda CDM and 1 if it's W0 WA cosmology. Then in that sense, you can actually run chains that jump between these two models and will give you a probability out in the end that says 67% confident, 67% credible interval that it is lambda, not the other. But again, the curse of Bayes' theorem strikes, and you need a prior to do this. And if you look at some of the results doing this, basically, it all depends on the prior you have. Whatever prior you put in, that say, for example, it's lambda CDM, changes your model probability of it being lambda CDM. So again, we're in this situation where the data is not sufficient by itself to tell us the difference models. And we can also define the Bayes factor, the ratio of the likelihoods, and try to make model determinations using the Bayes factor. I'm going to skip over that because I'm running out of time and I want to get on to frequentist methods. Okay. So when I started as a PhD student, we only did frequentist methods. Then gradually Bayesian methods came in, particularly with new big data sets and the ability of cosmology to basically constrain multiple parameters together using MCMC style techniques. But now people have realized that frequentist analysis has a place, and really we should be doing both frequentist and Bayesian analysis to get a good handle on everything. Okay. And I got an interdisciplinary grant, and I was talking to some statisticians, and I was expecting them to say, oh, you should always just do Bayesian analysis. But they definitely said, no, you should do both Bayesian and frequentist analysis. They tell you different things. You make different inferences about the universe from both of them. Why would you not do them both? So I think in the literature and in the field, we're seeing a return to this equilibrium where we're happy to do both Bayesian and frequentist inference. So the frequentist definition is interesting. It's after repeated experiments with confidence intervals defined by each using some procedure, whatever that is, the fraction of intervals that contain the true parameter will approach the confidence level of the interval defined by that process. The name and construction is a process for building classical frequentist confidence intervals. You look at the likelihood, and from the likelihood for a set of models, you calculate that models at the data point you have calculated. Then using some procedure, you define an interval based on the likelihood with a specified probability of it happening. And you do that for all model values, and you build a confidence band. Now, I'm going to explain this with an example in a minute, so don't worry if you haven't followed this exactly. So here's an example. We've got a model parameter mu, and we've got a measurement of it t. And we can calculate the likelihood, which is the value of the data given the model. So given the model, that means that basically we can define horizontal lines here as values of the likelihood. And you can think of this as being a contour plot of the likelihood. And this band being the standard 1 sigma 68% confidence interval of that likelihood. Now, if I measure one particular data point, I might look at those likelihood values for that data point, and I could use that as a procedure to define a frequentist confidence interval by saying I'm going to take the likelihood values where, for example, delta chi-squared is less than 1, and I will define that as my 67% confidence interval. I will take delta chi-squared less than 4 and define that as my 95% confidence interval. This is the name and idea. It's quite different from the Bayesian analysis. You haven't put in a prior. You're defining the intervals only using the likelihood. You're defining the intervals again in model space, but it is done only using the likelihood. And this is what you would traditionally do in the frequentist analysis, where you're looking at delta chi-squared of 1 confidence intervals. But there's a very interesting thing to note. Suppose now I told you that mu was something like the neutrino mass, where there is a physical limit that it has to be positive. And suppose that I measured a value that was -3. So my experiment had an error on it, and that error meant that I could measure a negative neutrino mass, even though I knew that the neutrino mass had to be positive. With this definition of the confidence interval, if I'm out here, my confidence interval is actually null, right? There is no confidence interval at all. That is completely fine in a frequentist sense. I've defined a procedure to calculate a confidence interval. I'm pretty sure that in a repeated experiment, 67% of the times the truth would be in that interval. But it so happens that for my particular experiment, I'm out here and my confidence interval defined by this procedure is null. Fine. What it actually means is you know that you're one of the experiments where the truth is not in your confidence interval because there's nothing in your confidence interval. But it's still a confidence interval. It would be very difficult to publish a paper saying that we made this measurement, we did a frequentist analysis, we had a null confidence interval, even though it would be statistically correct. And so with this in mind, this slide just says what I've just said. Feldman and Cousins developed a revised way of defining a confidence interval, which basically transitions nicely from having an interval through to an upper limit in these kind of situations where you've measured something that you know to be wrong. And what they said is that you shouldn't just define your probability that you're using to define the interval in terms of the likelihood. You should divide that likelihood by the best likelihood in the physical space of models that you're going to allow. So now the idea is if we go back to this situation, if we were out here, we wouldn't just say the interval is null. We'd have renormalized all of these likelihoods based on this value, the value at mu equals 0, which is the best fit physical value that fits our data of mu being like -3. And we would define the confidence interval as an upper limit in this physical space of models. Yeah.
Should I think of the experiment as one realization? Okay.
Should I think of the experiment as one realization of the CMB or the?
Sure.
Okay, rather than one measurement of it, I'm thinking of one example, like one CMB.
One set of data of it, yes.
Oh, okay.
And in this example, I think it's better if you think of one parameter, and I think it's better if you think of, say, a neutrino mass measurement, because that's the easiest one to think of where it's recent and we know that the neutrino mass has to be positive, unless you believe a few papers that nobody really believes. And it's also, we know it's possible for a data set to give you a data that suggests that you found negative neutrino mass. And in this case, you know that that model that is exactly on that data doesn't work. So in this sense of this realization, you would turn your measurement of -3 into an upper limit that starts at 0 and it goes only into positive space, but it's a redefinition of the likelihood. And this comes back to this idea that in a frequentist analysis, you just need to define some procedure of finding this interval and have this procedure work in that coverage probability % of repeated experiments. Okay. So what you will see, I think, in the literature over the next few months and years is an increased tendency to use both Bayesian and frequentist methods, and you will start to see Feldman and Cousins confidence intervals being used regularly as a way to define the frequentist interpretation of data. I'm over time, right? Yeah, 6 minutes. Okay. I will wrap this up very quickly. Strictly, one way of doing this in practice is something called the profile likelihood technique. This is a graphical method that's an implementation of the Neyman method. You can adjust it slightly to work with Feldman-Cousins. And what it does is what has traditionally been done. You look at chi-squared as the way of defining your confidence intervals from your likelihood. You do, for example, chi-squared less than 1 after maximizing the likelihood over all of the parameters that you're not interested in. So you define a profile likelihood chi-squared as the minimum where you've minimized over all of the other parameters that you're not interested in, and then you define a confidence interval based on some limit of that chi-squared value. And there's a theory, Wilt's theory, that says that this works in the limit of large data samples. But for non-Gaussian likelihoods, and particularly if you're doing Feldman-Cousins, you might have to go back and check the exact, using mocks, check the exact coverage probabilities of these methods. Okay. So increasingly in the literature, alongside Bayesian posteriors, you might start to see plots like this that give you basically confidence intervals on different parameters as delta chi-squared less than 1 intervals after using a Feldman-Cousins style technique to make those inferences. Okay. The final thing you should do, and a lot of people forget to do this, is to test the goodness fit of your model. So you've got your data, you fit a model to it, you've done it in a Bayesian and frequentist sense, you've got your confidence intervals, credible intervals. None of this has really told you, does the data actually fit the model? Oh, sorry, does the model fit the data? And this is worth testing. Classical way of doing this is to quote the chi-squared versus with degrees of freedom. There are other techniques out there. And in fact, a master's student working with me recently developed loopit, which is the leave one out probability integral transform. So ideally, to test whether a model fits the data, you might take your inference on one data set and make a prediction of what that would give you for a future experiment. Then the future experiment would tell you whether or not it matched the inferences you made from the experiment you are currently analyzing. We're often in a situation where we can't afford to do that. We can't take 2 experiments and compare one to the next. Instead, the leave one out idea is that you take each data point individually and you say, do the other data with the model and the posterior that you've got, do they predict that data point? And that's the leave one out. And then to say, do they predict, is basically, can you consider that data that you've left out of the analysis to be drawn from the posterior that you've basically derived from all of the other data? And to work out whether or not it could be drawn from that same posterior, we use the fact that if you divide a distribution by the expected value of the probability, then you end up with a uniform distribution. Any fluctuation in that distribution of points is removed by dividing by the expected posterior probability. And so you can develop these kind of techniques that if you apply this procedure to the data, you expect a particular uniform distribution out, which would tell you that all of the data points are consistent with the posterior you have derived. And so this is just one example I've gone through super quickly of the kind of tests of the data that you should then be doing. All of this in the end means that you can make robust statistical inferences from a set of data, which is what we need now, where there's a lot of debate in the literature about what data means. Does the DESI data actually tell you it's dynamical dark energy or not? This is exactly where we need these kind of statistical tests to do it. And I have to say, I think cosmologists and physicists are at the cutting edge of developments. We're at the cutting edge of statistical developments that are needed for physics and needed for cosmology, because the sort of problems we address and the way we do it is actually kind of different from the way, say, biostats works. There are some residual preferences, particularly against the reintroduction of frequentist methods. You will see people say that Bayesian is the only way and the only thing to do and the only way forwards. But I don't think that's the case. There are clear standard methods to use, and hopefully I've given you a little more understanding about why we're doing that. Okay, thanks.
Thanks, Will. 1 or 2 quick questions for Will? Yes.
Thank you for the wonderful talk. Model selection is a big part in cosmology analysis. So with the reintroduction of frequentist analysis, is there any place for model selection or at least understanding goodness of a model in the frequentist space?
There is space for model selection, certainly. I think model selection works better in a Bayesian sense than a frequentist sense. It doesn't quite work with these repeated experiments idea, but it does work with this idea of what is actually my understanding now of what the situation is. But what I've tried to emphasize in this talk is that you should do it all. You should not be put off from doing anything. But that's not really the case that one method is better than another. You should do it all and then take your inference from everything, because it's all really answering different questions. There is no real, is it frequentist better than Bayesian? Is Bayesian better than frequentist? That's a stupid, sorry, that's not a good question to ask, right? Because they're just asking different questions. Yeah.
All right, let's break for 7 plus or minus 2 minutes and thank Will again.
Yeah,
I'll leave that
got to be
to Will.
careful.